C2OH, or you can say C2H5O. What is this formula called, by the way? 6 actually. We would call it the molecular formula. Okay? Yeah. Whenever you see a whole bunch of carbons in there, call it the molecular formula. Okay? Yeah. This is the molecular formula. So when you're trying to calculate the weight, it doesn't matter how it's written, so long you account for all the atoms, okay, in there, because you need to put all the similar atoms together for ease of calculation. This is what you did so far, okay, is where you were given a formula and you calculated mass percents. Now we are going to do the opposite, okay, I got it. So now we're going to do the opposite, which is that if you were given mass percents, can you come up with the formula? Okay, and technically yes, okay, you should be able to. Because just like you were able to calculate mass percents, you should be able to do it the other way as well. Okay, so let's go ahead and do one of those problems. Okay. Determine the empirical formula if you have 52.15% carbon, 13.13% hydrogen, and 34.73% oxygen. In a compound. So now we're taking the reverse. First you did the other way, which means you had a formula, you were calculating mass percents. Now you have mass percents, you're going the other way. So the first thing you do for everything, 15.12% carbon, 13.13% hydrogen, and 34.73% oxygen. The first thing you do is add everything up. I think I missed something here. Yeah, there, 52.1. How did I even get that number? Okay, all right. So you take all of these numbers and you add them. And you can add them in your mind if you want to. You don't have to need the calculator for this, because you can round it off, and 52 and 13, that is 65, and 65 and about 34 is about 99. Okay, so which means that we are approximately 100%. Okay, in there. So that's the important part, because if we have 100%, it means that there is no mass lost. Okay, and I'll talk about the technique as to how we come up with these percents. All right, but the most common thing that is missing in there is the percent of oxygen. Okay, sometimes that's the only thing that is missing. Usually you will have the percent of the other elements, but not oxygen, and we'll come to that as to why it is. So then what you do is, since this is all a total of 100, you can presume that this is 100 grams of a substance, okay? So which means this is equivalent to 100 grams. So if this is 100 grams of substance, that means you have 52.15 grams of carbon, 13.13 grams of hydrogen, 34.73 grams of oxygen. One of the things that I mentioned to you in the last class, okay, is when you start looking at a formula like this, okay, when you have a formula like C2H6O, and you look at it, okay, I want you to look at this as a formula, but the other part is that I want you to look at each of these as, anyone remember? What was the key thing that we learned about last time? Moles. Okay, so I want you to look at it moles, which means that this is 2 moles of carbon, this is 6 moles of hydrogen, this is 1 mole of oxygen. Okay, and when you start looking at things in the mole quantities, then you know that you have to get to moles. Okay, which means that when you have gram quantities given over here, you know the next step is to go to mole. Okay, because here this is a ratio of 2 to 6 to 1. Okay, that's the ratio of elements here in moles. Okay, because remember, the gram quantity does not matter. Does anyone remember why the gram quantity does not matter? What was the thing about the gram quantity, which is why we don't deal with grams? It's because of?
How do I, not that the numbers aren't precise, just that certain elements weigh less, so you need more of them than other elements.
And more of what in them?
More proteins.
Atoms.
Okay, there we go.
Thank you very much. Okay, atoms. It was all about the atoms, okay? And the number we learned was last time? Yeah, 6.02 times 10 to the power 23. Avogadro's number. I was going to say that, and I think if I had said that, you would have known exactly what I was talking about, all right? But I wanted to get there on your own. So the number of atoms is really what's important here, okay? Because when you have a formula like C2860, it does not mean that you have 2 grams of this and 6 grams of hydrogen and 1 gram of oxygen. No, it has nothing to do with that. It has to do with the fact that you have 2 moles of carbon, and 2 moles of carbon means that you have 2 times 6.02 times 10 to the power of 23 atoms in there, okay? It has nothing to do with the mass, got it? So need to think like moles, okay? And then you will see that your calculations will become easier, which means that I need to convert all of these grams into moles to get my mole ratio, okay? It's not a gram ratio, it's a mole ratio. So which means I need to convert all of these into moles. So moles of carbons and grams of carbons. So my grams of carbon goes down here. And in 1 mole of carbon, how many grams do I have of carbon? 12. 12.011, right? Okay. That's from the periodic table. So then 1 mole of hydrogen has how many grams of hydrogen? 1.008. And then 1 mole of oxygen has 15.99 grams of oxygen. This is how you would do mole conversions also, which we're going to do a little bit more of today. I would have you do the calculation, and it does take a little while, so I have it for you. 4.25, 13.04, 2.2. Those are the numbers. That's your first step. That's what you have to do, is to find the mole ratio. Okay, when you're given the percent, you convert them into moles. So step number 1. Step number 2 is come up with the formula then, so which means that carbon is 4.25, hydrogen is 13.04, and oxygen is 2.2. Is that reasonable? Just a yes or no will suffice.
That's not going to work because whole atoms.
We need whole atoms, right? So this is not going to work, okay? Because you need to have whole atoms in there, okay? That's what Dalton's atomic theory said also, is that you have combinations of elements in a compound, but they should be whole numbers. So then how do we divide this? You take the smallest number that you have and you divide everything by the smallest number. So that's 2.2 divided by 2.2 divided by 2.2. Okay, so that's your next step, divided by smallest number. And that will give us C 2.2, H 5.9, and oxygen of course should be 1 then, at least one of them is 1 as a whole number. You still have decimal points, and now it's time to round off. Okay, because at this point, there is nothing else you can do but round off. So this is 2.2, so you round it off to 2. This is 5.9, so this becomes 6. And then oxygen is, of course, 1. You do not have to write 1. If you write 1, no big deal. Okay, but otherwise you don't have to write 1. So that's your final answer then. Okay, is C2860. It's a very simple calculation, and trust me, you're not going to miss it. Okay, I'm teaching it to you so much detail right now, but you will not miss this question, okay, at all, unless you really screw this up, which hopefully you won't, okay? But in any case, a very simple calculation to do, and then you get your empirical formula. This empirical formula can be translated into any molecular formula now, okay? Because if this is the empirical formula, I just need to multiply it with an integer, okay? Did you do question number 1? In the worksheet that I gave you? Question number 1 was the molecular formula of antifreeze ethylene glycol is C2H6O2. What is the empirical formula? Did you do this problem? Yes. Very good. So what did you do? You divided it by the lowest multiple. Okay, in there. So everything divided by 2. So which means that if you multiply this by 2, you would get the formula for this. Okay, for ethylene glycol. So how do you get this number? Well, you'll have to get the mass of this. Okay, I will have to give you the mass, okay, of something over here. Otherwise, you wouldn't know how to do this. Okay, so once you have the empirical formula, and I say, okay, well, the mass of the compound is what? 2 times carbon plus 6 hydrogen plus 2 oxygen, okay, which is, let's say, about 24 plus 6, and oxygen is 16, so that's 32. 30, 62. Okay, so I have to tell you that the mass of the actual compound is this much. Okay, so when you calculate the empirical formula, technically the mass of this formula should be half of this, isn't it? Because you had to multiply this by 2. Got it? Okay, so 1 carbon is 12 plus 3 and then plus 16, and that is 31. Okay, so once you know your empirical formula, you calculate the mass of that, and then I have to give you the mass of the actual molecular formula. Okay, so then the mass of the actual molecular formula, say, is 62, then you divide 62 by 31 and you come up with 2, and that's how you get that 2. Okay, there is no other way that you can get the 2. I have to give you the mass, okay, for this one. Otherwise, you wouldn't know, okay, what to multiply it with. So there is a problem like that here also, okay, that we'll do in a minute. Any questions about this so far? Okay, this kind of a problem, okay, that we just did, this is called combustion analysis, okay, or elemental analysis. Okay, and elemental analysis is when you're trying to figure out what elements do you have in a compound and what ratio do you have them in. Okay, so let me explain that to you a little bit. And this is not a theory, this is actually a thing. Okay, this is something that chemistry departments do. Okay, there is actually a machine which does all of this work, and what that is that you have a tube. Literally, you have a tube. And in that tube, you keep your sample, whatever your sample is, okay, and you heat it. And the heat can be anything. You can use a flame or you can use electrical heating. And then you pass oxygen over this. Combustion means something that is burning in oxygen. Okay, so you take this compound and you burn it in oxygen, and you just burn it with excess of oxygen. So once you burn something in excess of oxygen, every element in that compound is going to add on to oxygen. Okay, so if you have carbon in there, carbon will add oxygen to give carbon dioxide. If you have hydrogen in there, hydrogen will add oxygen to give you water. Okay, if you have sulfur in there, sulfur will add on oxygen and become sulfur dioxide. Okay, so everything burns and then everything just adds on oxygen to its formula. So you get all sorts of oxides, okay, in the final product. Then what you do is you translate this to, this is the grams, okay, that you will get. Grams of carbon dioxide, grams of water, grams of sulfur dioxide. Now everything is coming out all together over here, okay? So it's not like carbon dioxide is coming first and then water is coming next. No, no, no. That's not how it works. Everything comes out together and that goes through analysis. Okay, so you separate those out, then you figure out how many grams you have of each. So it's a little bit of an involved technique, okay, this elemental analysis. And then you take these grams that you have here for carbon dioxide, you figure out the grams of carbon from there. From grams of carbon, you figure out moles of carbon, okay? This is the part which we just did, by the way. Okay, remember? We started with percents, we converted that to grams. So grams of carbons to moles of carbons is where I kind of jumped in. but technically you start from grams of carbon dioxide. Okay, that's where you start from. So which means you have to convert grams of carbon dioxide to grams of carbon also. Okay, so this kind of a process really becomes a very involved calculation. Okay, it's not just a very simple one. It takes, it takes a little bit of involvement. It takes a whole page, okay, to do these kind of calculations. They're not hard to do. It's just tedious to do. Okay, it's a little bit involved because you have to go step by step. And if you miss even one step, then suddenly you're lost. Okay, then what do I do now? Okay, because I don't know where to go. So generally for our purpose, you will find that you have to do only these calculations. Okay, so you don't have to calculate grams of carbon dioxide to grams of carbon generally. So with water, it'll be the same thing. You calculate grams of hydrogen and then moles of hydrogen and so on and so forth. So when you are burning your sample in oxygen, what does oxygen give you? If you have oxygen in there and you burn that in oxygen, what does that give you? It's not a trick question. It really is not. Oxygen. Oxygen will give you oxygen. Okay, it's not a trick question. Okay, because oxygen will just give you oxygen. So if it's just oxygen, then you really don't know whether it's the oxygen coming from the compound or is it the oxygen that's coming that is excess of oxygen that you actually put in. Do you see what I mean? Okay, so you don't know where the oxygen is coming from. So what happens is, remember I was just telling you a few minutes ago that the only thing that sometimes misses is the oxygen, and that is because you will have the mass of this and this, but you will not have oxygen. So you will add these two up and make sure that they both come to be 100%, but if they're 80%, it means that 20% was oxygen. Okay, so the missing mass is usually oxygen if there is anything missing in there. Okay, and that's why you should always add up the percents. Yes?
You know how much oxygen you're putting into it, and you subtract it out.
No, you don't have to do all of that. It's really quite easy. By the time you get your products and you have the ratio of your products, you can just subtract it from 100. Okay, yeah, so it's easy to do. It's not the hard thing to do. Okay, yeah, yes?
So if you're burning oxygen with oxygen, are you constantly supplying it?
Yep, there's complete, just always the oxygen is always coming in, yeah.
Okay.
You have to have excess oxygen in there. So it's not like, no, it's not limited. Okay?
No, yeah, because I thought like fire would burn it up and eventually.
It does burn it, right. So, no, but there's constant flow of oxygen, constant. Okay, so oxygen is flowing through here, the products are flowing out through there. And everything is in gas state, okay, at this point. So that's why it's easy to then collect all the gases, separate them out, and then figure out how many grams you have of each. So it's a little bit involved process. I can tell you that when I was doing my PhD and I had to get elemental analysis done on my compounds, I never had to worry about doing this, actually. There's usually a technician who will operate the machine for you. Okay, and so it's an expensive machine. We didn't have it before, it came on later, but it's an expensive machine, so not everybody operates everything. Okay, there are some machines that you need, and not all the departments also have an elemental analysis machine. Okay, so it just depends on which department you're working in, and also what instrumentation they have. One of the things that we talked about in chapter 2 was a mass spectrophotometer. Do you remember that? We talked about how they figured out the isotopes, okay, that you have. So a mass spectrophotometer is going to tell you this number. So you put your compound into a mass spec, and it will tell you what the mass of your compound is. So once you know the mass of your compound, and you know the empirical formula, that's when you know what integer, okay, you have in there. So both of them work in hand, okay, and depending on which journal you're publishing in or where your research is going to go, you can either need the elemental analysis or you will need the mass spec. Okay, and if you have a really good mass spec, then you don't need elemental analysis. Okay, so it kind of goes as to what it is. You just need to know how to calculate a formula from mass percents. Okay, that's pretty much it for elemental analysis. Okay, so then let's go on to calculate a few things with what do you call moles. Okay, I want to do some conversions here with you. So calculate number of potassium atoms in 7.31 moles of potassium. And I hope it was not in this class where you gave me, was it the other one? I think somebody gave me P for potassium instead of phosphorus. I hope it wasn't in this class. No? Okay, good. All right, so calculate the number of atoms in 1 mole. So the mole factor that you need is that 1 mole you have 6.02 times 10 to the power of 23 atoms. I tell you, you're going to know this like anything. You have to know the exponent feature in your calculator. I told that to you even in chapter 1. So please bring out your calculators because we're going to just check if this works or not. So 7.31 moles of potassium times, and then you set up your conversion. You need to calculate atoms. So keep atoms on the top, moles down here, and in 1 mole you have 6.2, about 23 atoms. Do the calculation and tell me your answer, and then I'll tell you mine. I hope mine is correct. I don't know. Don't take too long. Do you have the answer?
4.40 times 10 to the 24.
10 to the power 24, yes. Atoms. Very good. And since we have 3 sig figs in our data, please make sure that you have 3 sig figs in the answer as well. Okay, so keep your answer consistent with the data significant figures. Okay. Then calculate the number of moles of potassium in 8.91 times 10 to the power of 25 atoms. Same kind of deal. I know I write fast, and this pen has absolutely no friction on the board, so it just flows. You don't even have to write calculate if you don't want to, right? What's the number of moles in 8.91? So now your starting point is 8.91, 10 to the power 25 atoms times, and now you need to calculate moles. Keep moles on the top, atoms down here, and 1 mole, 6.2. That's what I was telling you, that you can just reverse them in order to figure out, okay, what you need to have for your answer. So in this case, I'm just going to have somebody else give me the answer and get it in. Somebody else. Yes, one.
148.
Okay, we'll leave it to 148 because 3 sig figs. Okay, so 148 moles. I'm so innovative today. So how many grams of potassium? Poor potassium. It's going to be turning in its grade right now.
I'm going to go back to weight.
In 7.31 moles of potassium. So this is a gram to mole conversion. I just want to do all of these with you so you kind of understand how to approach the problems that you have to do. So in this case, the conversion factor you will need is from the periodic table, because you're talking about gram weight now. As soon as you have to find the grams of anything, please look at the periodic table. Keep that handy with you all the time. Okay, so in 1 mole potassium, there is 39.09 grams. Okay, and so 7.31 mole potassium times, what do I put on the top?
1 mole over 39.
What goes on the top? Grams. And the bottom is for moles, so I can cross that out. Okay, so in 1 mole I have 39.09 grams. Okay, that's how it is. And this is an easy calculation. This one I don't need help with. I just wanted to make sure you're getting your exponents right. This is where you'll need your exponents. If you did not get your exponents right over here in these calculations, please make sure you get help, okay? Either with me or Kevin or with any one of your friends. I think this one answer should be 286 or something like that. Okay, good, all right. So 286 grams of potassium. Always circle your answer or box them or something so you know that this is what it is. Okay. How many grams of, should we stick with potassium? Should we get potassium oxide? Okay, let's get potassium oxide. Now I've given you the formula over here as K2O, but I told you I'm never so kind, okay? It's very rare that I'm kind to you, especially with nomenclature. I'm not, because this is something that I really need you to know. So I will write potassium oxide, I will not write K2O, okay? So you have to know the formula for potassium oxide, and trust me, if I had not written K2O, you would be writing KO, most likely, no? No, okay, good, thank you, all right. So please make sure that you know your nomenclature well, okay? So if you're calculating grams of potassium oxide in that many moles of potassium oxide, your first task is to take K2O and calculate the grams in it. So you have 2 potassium and 1 oxygen. So 2 times 39.09 and then 1 times 15.99. Find that, add this up. Now this one I have not done, so I'll have to work this one with you. And so 39.1 times 2, 78.2, 15.99. And by the way, if you are bothered by the significant figures over here, let it go. Just let it go, okay? Because this is not your final answer. Your final answer is going to come after you finish all the calculations, okay? So don't start rounding off in the middle somewhere. I know significant figures are important, but not in the middle. So when you have these kind of calculations, just keep going with whatever you have, and at the end we're going to round off, okay? So please, mind that. So here we have this, so 3.90 moles times, and then again you have grams and moles. So now in 1 mole of K2O, potassium oxide, we have 94.19 grams. And
267. I didn't round till then. Because I came out.
So what did you get?
I got 367.
I got 283.
I got 367.
What did I miss? 94.19, right?
Mm-hmm.
Okay, 94.19 times 3.9. 367. I don't know what I did. Okay, so there we go. Good? These are your moles to atoms to everything conversion. If you were converting atoms to grams, so how many grams? Write shorthand, write your shorthand, beautiful shorthand. How many grams are in 2.98 times 10 to the power of 26 atoms? You can always take shortcuts, but you can take shortcuts only when you're comfortable. Until then, take everything to moles first, okay? So which means that if you have to go from atoms to grams, you go from atoms to moles to grams. Okay, that's what you should do initially. Later on you will become comfortable and that's fine. Okay, but right now this is what it is. So 2.98 10 to the power 26 times convert it to moles, so this is atoms. Atom goes at the bottom, moles goes on the top. So in 1 mole, how many atoms? 6.02 to the power 23. Yep, and then mole goes down and gram goes up there. So in 1 mole of gold, we have 190, let's just round that off, 197 grams of, like a horror story. Okay. Seems like a huge number.